All right, in this video we're going to discuss Magnus Effect and spin drift. Now these two things are connected to each other, so we're going to just tackle them both at the same time here. And there are some difficult concepts. If you try to read about this, sometimes it gets very confusing, but hopefully in this video we'll be able to kind of simplify it, and we might not get into as much depth as some of the more serious papers might get into, like the Army Research Laboratory when they're talking about some of the math equations and stuff. But we're going to go off of basic concepts here so that you can have an idea of what's going on and how you're going to have to be aware of this when you're doing your long-range precision rifle shooting. Okay, so before we get started talking about Magnus Effect, there is a little bit of review we're going to have to do on some airflow dynamic principles. There's a thing called Bernoulli's principle, and this has to do with inviscid fluids like air flowing at extreme velocities, for example. And we're talking about an increase of speed of the fluid is going to basically translate to less pressure. Decreased speed of a fluid is going to translate to more pressure. Think about like a garden hose. If it's going through there nice and fast, unobstructed, it's going to have less pressure. If you pinch it off and decrease the flow, you're going to increase the pressure. So that's Bernoulli's principle. And that has to do with wings of airplanes and all kinds of stuff like this, all different kinds of flow dynamics. Something to be aware of before we get started, because that's one of the driving forces of this Magnus Effect. And let's go ahead and define Magnus Effect here real quick. Some of you might not have any clue what we're even talking about yet. Magnus Effect is basically an effect in which induced pressure differences act upon a spinning projectile, which act in deflecting its course by twisting its axis of symmetry, the way the bullet is shaped, off of its axis of flight. So it's not going to be pointing the same way that it's flying. In other words, the way the air is flowing around the spinning bullet creates high pressure zones that push on the bullet's center of pressure, if you remember the center of pressure video, causing the bullet to fly crooked through the air. This is that yaw we were talking about. This yaw affects the bullet's aerodynamic stability, which can change the ballistic coefficient as the yaw changes, as well as affecting its direction of travel as that nose gets pointed off center. So that's basically, in a nutshell, Magnus Effect. Now, one thing to note here, too, is that the Magnus Force is always going to be perpendicular to the sideways vector of the wind acting on the bullet. So basically, whichever way the wind is acting on the bullet, 90 degrees from that is going to be the direction of your Magnus Force, depending on which way it's spinning and how the flow field dynamics are affected there. So let's look at the effects of crosswinds on bullet stability. Now, Magnus Effect is not only going to affect bullets that are just have winds applied to them, but it's also going to affect bullets flying through perfectly calm air. But we're going to first cover this. So the reason that the Magnus Effect has a significant role in bullet stability is because the Magnus Force does not act upon the bullet's center of gravity, but it rather acts on the bullet's center of pressure. That's where all the pressure is centered around the bullet, around the whole, all the different surfaces of the bullet as it's punching through the air there. That's the center of pressure like we talked about earlier. So that's going to affect the yaw of the bullet, because you got to remember the center of gravity is what's actually following the line of the trajectory. That's the direction of motion is determined by the center of gravity, the center of the bullet's mass. The center of pressure, if that's going to be different, that's going to torque off your bullet to the side. And the Magnus Force is going to greatly affect stability because it's trying to twist the bullet off of its flight path. And the place in where it gets its grip is on that center of pressure. So there's going to be kind of leverage going on there, fighting against that center of gravity, twisting that bullet off its flight path. And what we basically have yielded here, let's talk about crosswinds first. So if you have a right-hand twist rifle, most rifle barrels are right-hand twist. Sometimes you can have a left-hand twist barrel. If it's left-hand, it's going to be the opposite of everything I'm about to tell you here. But we're just going to do a right-hand twist as the example because that's kind of the standard. So for right-hand twist barrels, that's clockwise from the rear. If you have a wind coming from the right, the nose of the bullet is going to be shifted downward, perpendicular to the right-hand direction, into the axis of flight. So you got to remember that bullet is flying up, following the trajectory arc, and the axis of flight, if that nose wants to stay pointed in that direction, is going to have to constantly be bumped downward in order for that nose to follow that axis of flight. So actually, wind from the right is actually going to help to stabilize the bullet along its flight path because it's bumping the nose of the bullet on with the direction of motion. Now, conversely, a wind from the left-hand side on a clockwise bullet, a right-hand twist, the nose is going to be shifted upwards away from the axis of flight. So a wind coming from the left is going to act to destabilize the bullet. It's going to be increasing that the negative effects of those tractability problems we discussed earlier, where the bullet's coming kind of belly down through the air. It's going to be even worse if you have a wind from the left. So that's something to be aware of. Now, this vertical deflection that we're talking about here, this value tends to be very, very small in comparison with the horizontal values we're going to discuss in a second here. Another thing we're going to discuss is how yaw is caused by the Magnus effect. We're going to discuss how that works, and that's actually what causes most of our spin drift. In right-hand twist barrels, bullets are going to drift to the right. In left-hand twist barrels, bullets are going to drift to the left. Pretty simple to remember there. Now, this is not hemisphere specific. It doesn't matter which hemisphere you're in or what direction you're pointing. This is purely having to do with pressure forces acting on the bullet on the center of pressure. Coriolis is not to be confused with Magnus Force, and we'll get into Coriolis effect later on here. So let's discuss real quick how Magnus effect works. So we talked about Bernoulli's principle and the flow field dynamics. So because of the bullet's spin, the flow field flowing around that bullet becomes kind of asymmetrical. Let's look at a picture here. As let's say we have wind coming in from the right-hand side, and the bullet is going away from you. It's a right-hand twist, clockwise motion from the rear, okay? And you can see here the wind's coming in from the right. Now, if you notice on the top side, where the wind is kind of going against the direction of the surface of the bullet, it's spinning clockwise. So the bullet's spinning on the top side to the right. That surface on the top side is going to the right, but the wind is coming from the right, so it's going to the left. So that the surface of the bullet is fighting the wind. Now, on the bottom side of the bullet, the flow field is going along with the direction of the spin of the bottom side of the bullet. It's going away, so they're both going in that direction. So what we have here is molecules of the airstream are adhering to the bullet's surface if you get really close. Bernoulli's principle says that higher streaming velocity corresponds with lower pressure, and also lower velocity with a higher pressure, right? We just talked about that. So what we have happen is we have air gets jammed up on that top side where it's fighting against the spin of the bullet, and that's going to create decreased fluid flow, which is going to correspond with high pressure zone. On the bottom side, you have the air going along with it, so they're both going real fast, so that your overall fluid flow is higher on the bottom side, and that's going to basically result in a lower pressure. So if you have high pressure on one side and low pressure on the other side, guess which way the bullet's going to be deflected? Away from the high pressure, right? So the Magnus force is acting this way. In this case, a wind coming from the right-hand side going towards the left, the Magnus force is downward towards the area of low pressure, the area of higher airflow. Now, this is going to be opposite if you have the bullet spinning in a left-hand twist. If it's in a left-hand twist, then those arrows going around and around in circles are going to be pointed the other way, so your flow field is going to be opposite. In that case, your Magnus Force would be upward. So that was the vertical deflections we're talking about in regards to Magnus Force. A deflection either down or up due to wind coming from the right or the left. Standard crosswinds will cause very minor deflections up and down. Now, the actual magnitude of these vertical Magnus corrections is very, very, very small. It does slightly affect your bullet's aerodynamic stability and your ballistic coefficient. If your bullet is more stable due to a wind coming from the right-hand side, pushing the nose of the bullet downward, that's going to cause it to fly more in line with the trajectory. So it's going to be more efficient in its flight. So you're going to have slightly less drop. Not hardly enough to measure, though, especially when compared to all the other factors that are going to cause vertical deflections, such as muzzle velocity variation, atmospheric density variations, and the like. Those things are going to have a much greater effect, and they're actually going the wiggle room in the degree of precision which you're going to be able to even measure the atmospheric density, for example, or the ammunition temperature muzzle variation, for example. Those things are the wiggle room in there even is going to dwarf in comparison to the corrections that you would apply for a vertical Magnus Force. So it's not something that most shooters are going to be correcting for. It is something you do want to be aware of. It is good to know how the wind is affecting your bullet stability. That will affect slightly your max range, or it might just bump you up or bump you down just a little bit on that as far as stability goes. When we're talking about if you want to make a transonic shot or not, this will have a tiny bit of effect on things like that. But as far as actually correcting vertically, this is too small to correct for. Now, another thing to just mention here is note that these sideways wind forces are causing a vertical deflection. It's perpendicular with the direction of the wind. So it's not like this is going to cancel out your wind. It's bumping it up and down instead of left and right. You know what I'm saying? So that's just something some guys get confused about which direction this Magnus Force is. It's always perpendicular to the vector of the wind, okay? Okay, so that was Magnus Forces when we're talking about a crosswind. And those forces were vertical, okay? Now we're going to talk about Magnus Forces where there is no wind, okay? So as the bullet flies along its axis of motion, gyroscopic forces are going to be fighting to keep the bullet's spin axis rigid in space, like we talked about earlier, at that original angle of departure, kind of at an inclined angle. Now, at the same time, there's going to be a zone of high pressure developing along the side of the bullet, which is the most out of line of the axis of flight, okay? This compressed high pressure zone is going to be constantly pushing the bullet's nose back into the direction of flight along the arc of the trajectory. So you got to take into effect the arc of the trajectory, and in order to create a nice even flow on both sides, there's going to be a downforce. This is called a weather vane effect, and this is acting on the center of pressure. It's not acting on the center of gravity or what we call the center of mass of the bullet. This is acting on the center of pressure located in front of the center of gravity. So this is going to push the bullet's nose downwards into the axis of the bullet's motion through the arc of the trajectory. Now, this downward force on the bullet creates another Magnus Force, which is perpendicular to the vector of the downforce, okay? Now, this is on a spinning bullet with the right-hand twist. It's going to be perpendicular to the downforce, so it's going to experience a Magnus Force acting on the center of pressure to the right. So basically what we going on here is as the center of mass of the bullet, also known as the center of gravity, continues to follow the line of the trajectory, the nose of the bullet, being yawed to the right, causes that thing to begin to veer off its original flight path and drift to the right, because it's pointing to the right. That's one of the main things that's the contributor to what we know as spin drift, okay? There's also some other things going on here. One of the other big things contributing to the sideways drift of the bullet, besides the Magnus effects, which we just discussed, is that as the bullet is still oriented slightly nose up, especially as it proceeds belly down through the descending branch of its trajectory, the molecules of the airstream encountering the bottom side of that bullet, still spinning at like 200,000 RPMs or more, or whatever your spin rate would work out to be with your velocity, causes an additional drift to the right. So it's coming belly down through the air during that descending leg, spinning clockwise, so that bottom side's rubbing against the air, and that's going to cause an additional drift to the right, in addition to the yaw. So there's several things going on here, and if you were to map out all the different forces, the atmospheric forces, the different pressure differentials, and all the different vectors of the momentum of the bullet flying just forward on its trajectory arc, it becomes quite dynamic, and it's very hard to illustrate even. So there's a lot of different things affecting each other here. But let's take a look here one more time. So here we have the figure of the bullet's axis, and you can see there that the center of gravity is what's following that bullet's axis. That red line is the bullet's axis. The center of gravity is the center of the mass of the bullet. And like we talked about before, the front of the nose is going to experience this down force labeled in the blue here, and that's going to be that's a weather vane effect. That's going to try and push that thing down so that it's an equal force on all sides. It's due to the shape of the bullet. Now, if you mess with the shape, this down force is going to be severely altered. But on most bullet shapes, the shape of that ogive and the contour, it is kind of self-stabilizing aerodynamically up to a certain point. Once you exceed a certain amount of degrees being off of the axis of flight, then bad things kind of start to happen, which are extremely difficult to even correct for. Then you have aerodynamic instability going on, and the math problem now takes up 10 pages. But what we see here is the down force is pushing down on the center of pressure, so that's acting as kind of a lever against that center of gravity being the hinge following that trajectory line, and that's pushing it downwards, okay? So that down force, that's a pressure acting on the center of pressure, that's going to have a perpendicular Magnus force, okay, resulting from that. And that Magnus force, based on the spin of a right-hand bullet, is going to be to the right. Now, if this was a left-hand spin on this bullet, that side force would be to the left, and your spin drift would also be to the left then. So that's something you want to pay attention to when you're selecting your rifle barrel or when you pick up a new rifle. If it's a right-hand twist, expect the bullet to drift to the right. If it's a left-hand twist, expect it to drift to the left. So another thing to take into consideration here, and it's just noteworthy, is that the longer a bullet is, the more the airstream comes into contact with the longitudinal axis of the bullet's surfaces, thus the more the airflow is disrupted, affecting the bullet's center of pressure, increasing these Magnus effects. And also another thing with long bullets is that the longer the distance is between the center of gravity and its center of pressure, thus increasing that leverage, that moment arm between the two, and it basically results in greater susceptibility to twist the bullet off its axis of flight due to these pressure-induced Magnus forces. And we hinted at that a little bit on an earlier video when we're talking about long-range bullet profiles and how they're a little bit harder to stabilize aerodynamically due to things like this. But as we discussed earlier, the advantages of a VLD-style bullet, which happens to be pretty long and sleek, are still much greater than the disadvantages. So that's why we still opt to go for the long, contoured, VLD tapered rear-end type bullets. So just something to make of note there. Some people might wonder, why the heck would you use a long bullet if it's going to be destabilized in that fashion? But like we said earlier, ballistic coefficient, the overall ballistic coefficient is still much greater just due to the shape and the profile. So how do we correct for these Magnus forces? Now this horizontal Magnus force correction, which is basically torquing that bullet and giving it that yaw of repose like we showed you on this video earlier, that's going to cause spin drift. That's something that's going to be significant. You're going to have to correct for that. Unlike the vertical Magnus forces earlier, which we said were too small to really worry about, unless you're shooting 10 or 15 miles with field artillery, it's not something to worry about. But the spin drift is definitely something you're going to have to correct for. This can throw you off by a foot or so at 1,000 meters and maybe a little more even at longer distances if you're reaching out that far. So just as an introduction here, and we'll get into this more on the next video, I'll actually get you guys set up to correct for your spin drift. There's lots of different ways you can mathematically figure this out, but probably the most common way to do it is Brian Litz's formula. And he wrote it in, I believe, a book called Applied Ballistics for Long-Range Shooting or something like that. And you can figure out your spin drift in inches by a simple formula involving, you got to have the Miller stability factor for your bullet. And we discussed that on a video earlier. And if you remember, that was kind of a bugger of an equation, okay? And you have to figure out the time of flight. Once you have the Miller stability factor and the time of flight, you plug it into this formula, and you get your spin drift in inches. And you would most likely want to convert those inches into an angular correction, like minutes of angle or milliradians, so that you can index that correction on your optic more precisely rather than guesstimating just by looking at the target. So you can do it by hold off, just by looking at guessing the inches, but it's always best to index it. So the nutshell of that whole situation is that that gets to be kind of complicated to do in the field. You can do it in the field if you're awesome, but for most of us, myself included, you're going to want to develop a spin drift table, basically, that's going to just tell you kind of where to adjust, because trying to figure out your Miller stability factor for all your different possible muzzle velocity regimes for your different your ammo temperatures, and also trying to figure out your time of flight for each different range and each different air density is going to be a real bugger to do on the fly while the target's running away from you. So that's something you're going to want to have burned into your brain. And if you it's really pretty simple to remember. It's a relatively constant kind of deal for a given twist and bullet and rifle, because your time of flight doesn't vary that dramatically. But we'll get you a real precise way to correct for the spin drift using Microsoft Excel. And there's also, I would recommend, if you can also use JBM Ballistics like I showed you earlier, and they do have a function on there to figure out your spin drift corrections. So you're going to want to use software for this and then print it up or write it down. If you don't have a printer, just write it down in a notebook, your spin drift corrections chart, because that's something that you're just not going to be able to correct for on the fly in the field. So in the next video, I'll show you how to figure that out and get the computer to do the math for you so that you don't want to pull all your hair out. All right, stay tuned for the next video. We're going to show you how to calculate your spin drift tables.
Sun, I recall the days when the feeling was warm.